Alright, when we're trying to test for two different variables, we're going to take ordinal pairs of data from each, an x value and a y value, and try to determine if there's a correlation between the x variable and the y variable. Now specifically, we're going to look for a linear correlation between the two. And our linear correlation coefficient is the value r. This is a statistic that measures how strong a linear relationship is. Now, here's a couple examples of scatter plots. One of the first things that you should do when you're trying to determine if there's a correlation between two variables x and y is you're going to look at a scatter plot of the data. These would plot just like normal. This is a Cartesian plane. The x values are the horizontal axis, the y values are on the vertical axis, and each of these points has both an x and y coordinate to it. Now you can see from this set of data here, in my left chart, chart A, that as x goes up, so does y. There's an incline, and you can see sort of a trend that goes up. So as x goes up, y goes up. So the r value here is 0.851. The highest possible value the r value can be is 1, which would be a positive correlation where every point would be on the actual line. So this is a pretty good correlation. So it's a pretty strong correlation. There's a lot of points here. 0.851 is pretty large for that. Now conversely, the chart B, as x increases, y actually decreases. So you see a downward slope as far as the trend is concerned. And the negative correlation there is negative 0.965, an even stronger correlation only towards the negative realm. So a negative 1 is the lowest possible value that the r value can be, and that's when they're all on the line when they're going down. As you can see, these are more tightly packed together than these. These are a little bit more spread out. That's why this is a little bit less than 1 than this is above negative 1. So this is just a stronger correlation even though it's negative. Now, the plot in C has no correlation, or a correlation value of r that's close to 0. There doesn't appear to be an upward or downward trend, and none of the data really seems to form any sort of pattern. It's just kind of a big mess in there. So that's when we have no correlation. So our r value can basically take three values: a value close to 1, in which case we have a positive correlation; a value close to negative 1, where it's a negative correlation; or a value close to 0, when then there's no correlation. Now, here's an instance, part D, where we have no linear relationship. We have an r value very close to 0. It's negative 0.087. However, it's very clear from looking at this data on a scatter plot that there is a correlation between the two. It just doesn't happen to be linear. Linear would imply a straight line. This one is more of a parabola. So it's probably a quadratic relationship as opposed to a linear one. So it's always a good idea to take a look at your data before you run anything. So you take a look at the scatter plot first. So our requirements to find a correlation between data sets is we have to have paired data. We have to have, for each data point, there has to be an x and a y. And it has to come from quantitative data. Number 2 is what we just talked about. We have to look at the scatter plot and confirm that a straight line pattern is appropriate. The third one, if you know an outlier is there and it's because of some sort of error, it should be noted and the outlier should be removed. Now, you can't just start taking out outliers for no reason. Specific outliers are going to really influence our correlation. It's not resistant to extreme values like the median would be or something. And now our properties of our correlation coefficient r, and again this is a linear value. As I mentioned, the lowest possible value can be as negative 1, and it achieves that when you have a perfectly straight line that goes downward, and it can go as high as positive 1. Now we can change the scale of the model. say you're running car values in the thousands of dollars, but instead of wanting to put in 10,000, you can use the number 10, run the regression, and those would extrapolate, and the R value would be the same if it had been 10,000 and 10,500. You'd use 10 and 10.5 and so forth. So you can change the scale and it won't change the R value. We can also flip-flop the X and Y. If we decide to flip it around, the R value isn't going to change. It's still going to have the same correlation up or down. R simply measures how strong of a linear relationship it is. Again, the parabola that we showed, it doesn't have a linear relationship, so it had an R value close to 0, but it did have a relationship of some sort. And our R value is very sensitive to outliers. If you put in one value that bucks the trend significantly, the R value will have a dramatic effect.